Hello. Last time we have discussed the F test or the variance ratio. Today we are going to analyze ANOVA. ANOVA, ANOVA, which means analysis of variance. This is particularly critical from the point of view of multiple samples out of the same population or out of different populations. The universal set may be either one, it can be more than one. So we have to take samples out of either one universal set or out of many universal sets, but anyway the test will continue on the assumption that many groups, many samples contained in the primary analysis data. Because of that, we are not in a position to use the t-test, because t-test can be applied only when there is two samples. So when there are more than groups, two samples, we are required to use ANOVA or analysis of variance, and this is done by a completely randomized design. Researchers many times are confronted with the situation when the samples are derived from several different populations. For example, each of three different variety of rice or variety of wheat, and it is of immense interest to test the null hypothesis. The population means are all the same for all the different samples derived from different populations. The technique which is used, because of the difference in population, we are not in a position to include and test with t because of the varied size of the sample. So the technique that is going to be used is known as ANOVA, and we are going to test whether the same population mean and variance is included in all the two or three different populations that we are discussing right now. So which means if rice is cultivated over three different pieces of land, you have to calculate whether the product which has been derived as a result at the end of the cultivation season are actually having the same kind of mean or same kind of variance. So because you are taking more than two samples, so you should be using ANOVA, but instead of using ANOVA, we actually can and should be able to use multiple t-test also, because t-test is able to calculate and summarize the hypothesis testing between two sample means. So we can have multiple t-tests, like one t-test between 1 and 2, one t-test between sample 2 and 3, and another t-test with sample 1 and 3. So there should be the requirement of 3 sample t-tests in case of 3 population or 3 samples derived from the same population. Here, instead of doing that, we can do utilize actually one test which is called and goes by the name of ANOVA. This because it has non-specific causes like variable land, seed, variable cultivation practices, different kind of rainfalls, different kind of machines used, differentiation between the pesticides used. These will create non-specific causes. All these causes are going to be included, going to be present there, but we don't know what kind of cause is actually going to have a particular effect on the amount of the result. On the other hand, if the varieties had different population means, but the same population variances, then one would expect the variability between plots with different varieties greater than that for the plots with the same variety. Hence, the idea of ANOVA is to compare the variability of plots receiving different treatments to that of the plots receiving same treatment. So in case you are using the same kind of population, then what happens is there a significant chance that the mean which is occurring to the similar kind of data sets are actually going to be any different from dissimilar kind of populations. So that is the gist of ANOVA. We can take the following assumptions to be present. Each population has a normal distribution, so each population is assumed to be normally distributed, and population from which the samples are drawn has actually equal amount of variances. So the standard deviation and the variance actually going to be equal. Each sample is drawn very randomly and is independent of the sample, so there is no correlation, there is no pre-summarized analysis by the investigator into the same kind of population. So there is is why how the samples are drawn very randomly. Treatment effects are required to be additive, means they differ by additive amounts but not by multiplicative factors. So treatments are generally not repeated randomly. Failure to satisfy any of the four assumptions affect both the level of significance, that alpha, and the sensitivity of the F test. So all these assumptions has to be satisfied, has to be met with. There are two kinds of ANOVAs. One is one-way ANOVA and the second is two-way ANOVA. One-way ANOVA examines whether multiple means actually has different variability, whether they differ. The test is called an F test. ANOVA calculates the ratio of the variation between groups of variable groups that lie within the same population or lie between the same population, which means we can use F ratio if it is within the group or between the groups, which means there is one or two or three groups. Two-way ANOVA allows for a second independent variable and addresses the interaction between two such different variables. We will discuss two-way ANOVA in a different session. The F test assumes that the group variances are approximately equal and that the observations are independent of each other. It also assumes normally distributed data. However, since this is a test on the means of central limit theorem, it holds true so long as the sample size is not too small. So for the ANOVA to be complied with, we little bit assume, there is a little bit assumption that central limit theorem do hold as a whole. ANOVA is easy for analyzing data using a low and relatively few number of trials and can be used with categorical variables. So different category variables can be sustained through the test of ANOVA. You can note it very seriously that regression can perform a similar analysis to that of ANOVA. So you can do a regression analysis over different kind of groups, calculating the correlation coefficient and regression coefficients. Analysis of variance actually uses a completely randomized design. A completely randomized design is one in which the three treatments are assigned completely at random. So each of our experimental unit has the same chance of receiving any one treatment, which means for the completely randomized design, any difference amongst the experimental units receiving the same treatment is considered as experimental error. In CRD, that is a randomized design, the total variable in the data as measured by the total sum of squares is partitioned into sum of squares within and sum of squares between. So the total variability is measured as ST. SST is equal to SSB and SSW, sum of squares between and squares within. So both of them added together will be able to calculate the sum of squares, total sum of squares lying with the same set of sample, lying with the same set of population variances. The sum of squares within, rather between, is a measure of the difference of different means. So how you treat the means of different series are actually going to be calculated between, because we are going to calculate as many means as the number of samples is. The second is sum of squares within, which is a measure of the differences in the observations within treatments, which is due to experimental error. So the second is SST is equal to SSB plus SSW. There is a total degree of freedom which is known as n-1, which is there are two degrees of error. One is the sample error between degree of freedom of sample with the variables, that is n-1, and when you calculate the degree of freedom within the samples, that is n-k. So by subtracting pluses, we get n-1. When these sum of squares are divided by associated degree of freedom, the first one is having the degree of freedom of n-1 is the between sample, then it has a degree of freedom of n-1. So mean square between is equal to sum of squares between divided by n-1. Mean square within is sum of within divided by n-k, and mean square total is sum of squares total divided by n-1. So there are three calculations which has to be done with the help of these formulas. Now after calculating MST, MSD and MSW, we can be able to calculate the F value. So F, the variance is calculated with a K minus 1 degree of freedom for the numerator and N minus K degree of freedom for denominator, provided we can calculate F as SB upon K minus 1 divided by SSW by N minus K, that is MSB by MSW. So the value of F, the variance ratio, can be calculated as the decimal of MSV upon MSW. This is going to be regarded as the calculated value of F. Anyway, we have to consider the calculated value of F should be less than that of the table value of F, which we are obviously going to find out from the table given to you, supplied to you. Following the decision rule, once you have the calculated value with us with the help of F is equal to MSB by MSW, then we have to find the table value. If the calculated value of the F test statistic is more than that of the right tail critical value of F for a degree of freedom of N minus 1, then we reject the hypothesis, which means if F calculated value is less than F table value, we accept the null hypothesis. If F calculated value is more than F table value, we reject the null hypothesis. We accept the alternative hypothesis which is given to us by way of the table. So the decision rule is almost similar to that of T and Z test. So whether it's a small sample test or a large sample test, we use similar kind of decision making process. This has been summarized into the followings: the sum of square of variation, sum of square of square, degree of freedom, mean square and test statistic. We have to summarize the table like this. We find the SSV, SSW and then add together to find the SSV. The degree of freedom is taken as, for SSV it is K minus 1, for SSW it is minus K, and for SST this is N minus 1. You can calculate mean square by dividing SSV with K minus 1 and SSW with N minus K, that is MSW. The value of F can be calculated as MSB divided by MSW. This will be the F calculated value, and we are going to compare that with the F table value which we calculated with the given value of tables with a particular amount of level significance having N minus 1 degree of freedom. We're coming to the numerical part of the study. A study which is investigated in the perception of corporate ethical values among various individuals who are specializing in marketing. There are three kind of people: marketing managers, marketing research people and advertising people. We are using a 5% level of significance. Following data had the score, had the ethical value, test for the significant difference in perception among three groups. Marketing manager has a value of 654,564. Marketing research has a value of 55444. Advertising is 6 and 7, 6 and 5, 6 and 6. Let us assume the hypothesis that there is no significant difference between the ethical values among all the individuals specializing in marketing, only in three groups. So there are three groups drawn from the same population. The calculation for the analysis variance is given as follows. We take marketing managers values as x1, marketing research values as x2 and advertising values for x3. So marketing managers x1 values is 654564. We calculate x1 square. 6 square, that is 36, 5 square, 4 square, 5 square, 6 square, 4 square. We calculate the total x1 and x1 square. X1 is the summation of x1 is coming to be 30. Summation of x1 square is coming to be 154. Similarly, we take marketing which as x2. The values are given as 554454. We calculate x2 square. The summation of x2 square is coming to be 123. x3 values are given as 676566, and x3 square values are given as 3649, 3625, 36 and 36. So the total of the values is coming to be 218. We're going to use these values to find the correct factor, which is the experimental error. The sum of all the observations in the three samples is 30 plus 27 plus 36. There are 18 samples in all, so the value is 90. The correction factor is t square upon n, which is 93 square by 18, that is 4.5. That is the error that can creep into the entire story. We then calculate the SST, sum of squares, total of sums, which is summation of x1 square plus summation of x2 square plus summation of x3 square minus correction factor. x1 square, the table is given in the last slide, is 154 plus 120 plus 218. Minus the correction factor, 480.5. So SST is summation of all the individual squares plus the second plus the third minus the correction factor. So the sum of squares total is coming to be 14.5. Now we calculate the sum of squares between the samples, that is x1 square by n1, x2 by n2, x3 square by n3 minus the correction factor. 30 square by 6, 37 square by 6, 36 square by 6 minus 480.5. The value is coming to be 7. So SSB is coming to be 7. SST is given to be 14.5. SSB plus SSW is SST. So SST minus SSB is SSW. So SSW is coming to be 14.5 by 7, that is 7.5. So continue to find the degrees of freedom. The total degree of freedom, the degree of freedoms for between and for within. For between is denoted as V1, which is k minus 1, and V2, which is n minus k. So all in all, this is k minus 1 plus n minus 1. So k minus 1 is 3 minus 1, that is 2, and k is 18 minus 3, that is 15. So MSB can be calculated as SSB by degree of k minus 1. So 7 by 2, that is 3.5. MSW is SSW by V, 7.5 by 15, that is 0.5. So we have mean square between and mean square within. Now we summarize that in the form of a table. The sum of squares value is 7, SSB, degree is 2, that is k minus 1, and k number of types of samples, that is 3 number of samples. So mean square between is 7 by 2, that is 3.5. Mean square within is 7.5 by 15, that is 5. Total is 14.5, and total degree of freedom is 17. Test statistics F is calculated as B by MSW. So that is 3.5 by 0.5, which is 7. So F calculated value is 7. The table value for F for V1 and V2, V1 of 2 and V2 of 15 for a of 5% is given to be and found to be 3.68 from the table, ANOVA table. Since the calculated value is much greater than the table value, the null hypothesis is rejected because the value is higher. So calculated value should be less than the table value for the hypothesis to be accepted. So because the calculated value is almost that of the table value, the null hypothesis is required to be rejected. Hence we conclude from the testing there is significant difference in ethical values among individuals specializing in marketing in that particular company. So whole in all, we must continue to shift our focus to the table. You calculate ST, you calculate the correction factor, you calculate SST, then calculate SSB, calculate SSW. After finding these two, you summarize them in the table. So calculate MSB, calculate MSW, divide MSB by W, find the F value. So once you find calculated value of F, you should proceed on to calculate and find the table value F from the table which is given and compare that. If the F calculated value is less than F table value, we accept the null hypothesis. The calculated value is greater than the table value of F, which of course we have got from the table, then the hypothesis is ought to be rejected. Now we are coming to the next set of questions. We included 4 samples here, 4 samples. So there are brand A, brand B, brand C and brand D, 4 samples each. All in all, it has 12 samples. Number of samples are 12, whereas in the previous question there are 3 samples of 6 samples each. So within the sample there are 6 samples, so there were 18 samples, but here 12 samples in all. As the head of the department of a consumer research organization, I have the responsibility for testing and comparing financial lifetime data of 4 brands of electric bulbs: brand A, brand B, brand C, and brand D. Suppose you test the lifetime bulbs of each of the 4 samples or the brands. Data is given below. Brand A has 20, 19, and 21. Brand B has 25, 23, and 1. Brand C has 24, 20, and 22. Brand D has 23, 20, and 20. Can we infer from the above data that the mean lifetime of the 4 brands are equal? So this sounds very similar to that of t-test. We have to compare the means, but you can see here, instead of 2, which can be computed under t-testing, here there are 4 brands. We can include 4 brands in t-testing, 4 samples in t-testing. So that's why we are bound to use ANOVA. First thing, we prepare the table x1, we take the first value, we take brand B as x2, brand C as x3, and brand D as x4. So after calculating the summation of x1 and x1 square, we proceed on to calculate x2 and x2 square, then x3 and x3 square, summation of x4 and x4 square. We need all the summation of squares as given in the analysis table in the question. The data are given, so we have to calculate the values. Now we have to find out the sum of all observations in all the 3 samples. 0 plus 9 plus 6 plus 3, which is coming to be 18. The correction factor is coming to be t square upon n, that is 18 square by 12, which is 27. Now we go on to find out the sum of squares total, which is summation of x1 square plus summation of x square plus summation of x3 square and summation of x4 square minus the correction factor, which is coming to be 27. So 2 plus 35 plus 20 plus 9 minus 27. So we are getting the SST as to be 39. Once you have the SST, we should proceed now to find the SSB, which is x1 square summation of x1 square by n1, x2 square by n2, x3 square by n3, and x4 square by n4. By 3, 9 square by 3, 6 square by 3, 3 square by 3 minus 27. So by analyzing and simplifying the equation, we get SSB as 15. We all know that SSB plus SSW is SST. We are given SST, so by subtracting SSB from SST, we get SSW. So the SSW is 39 minus 15, which is 24. The degree of freedom is k minus 1, that is minus 1, which is 3. And we have 12 samples, 3 samples of 4 each. So V2, degree of freedom 2, is 8. So MSB is SSB by 1, which is 15 by 3, 5. MSW is 24 by 8, that is 3. We summarize all this, whatever we have calculated, into right now. We have got sum of squares between as 15, degree of freedom of the sum of the samples as 3, mean square coming to be 15 by 3, that is fine. Sum of squares within the sample is coming out to be 24, and the degree of freedom is coming to be 8. So the mean square within is coming to be 3. So after we calculate the mean square between mean square within, we calculate the value of f. F calculate value, which is coming to be MSB by MSW, that is 5 by, which is coming to be 1.6666, which can be summarized as 1.667. So we have got the calculated value of f. Now proceed on to calculate and find out the table value of f. We have 2 degree of freedoms. One degree of freedom is 3, and the other degree of freedom is 8, and the alpha or level of significance of the test is 5%. The table value f for a degree of freedom for the first series, which is for the degree of freedom V2, which is 8, for a level of significance of 5% is coming out to be 4.07. Since the calculated value of f is 3 and it is coming to be less than that of the table value, the null hypothesis is accepted. Hence we conclude that the mean lifetime of the 4 brands are not significantly different. So we infer that average lifetime of the 4 brands are almost equal. So we have done both the examples. Now to the theoretical. I have told you in a simple manner that if we have 2 samples and we have to calculate the variability of these mean variance, then we must use the t-test. But t-test might be very unreliable because it is not under normal circumstances to use t-testing for more than 2 samples. If we only compare 2 means, then we have to find multiple t-tests. But instead of doing multiple t-tests, one answer are going still to be the same. So it is used, ANOVA is used to compare the means of more than 2 samples. This can be understood with the example. We will test the effect of 5 different exercises. For this we recruit 20 men and assign one type of exercise to 4 men, which means there are 4 people each. Their weights are recorded after a few weeks. We find out whether of these exercises is significantly different or not, and this may be comparing the weights of these 5 groups of 4 men each. The example is of one-way balanced ANOVA because we cannot find 5 t-tests out of it. That is very cumbersome. It has been termed as one category whose effect is being studied. The balance number of variables are remaining same throughout the study. So the basic idea is to test samples are all alike or not. But the question is, why not we conduct multiple t-tests? Because t-test is simple to calculate, simply very beneficial to understand. So why not multiple t-tests? But conducting multiple t-tests in a general format can lead to severe complications. And in such circumstances we use ANOVA. What happens is, if there are 5 groups of 4 people, we have to calculate one test between group 1 and group 2, another group 2 and group 3 and 4, 4 and 5, then 5 and 1. So we have 5 t-tests, t-values. So we are not conducting the test all of the 5 at the same time. We are conducting one upon other. There are 5. But how to interpret the 5 results? So because of the question asked about the whole group, whole sample universal population, we need to calculate and deviate from 5 sample t-tests to be able to calculate one standard ANOVA test. So ANOVA is a technique which is used whenever an alternative procedure is available to that of the test, and whenever there is more than 2 normally, no more than 2 populations existing on the same breed, and you were actually asked to calculate those things at the same place, then we are going to use in the first place. Now the question is, what do you mean by one-way and two-way ANOVA? One-way ANOVA means one of the things remain constant. We are concentrating on the same factor from the perspective of being finalizing the testing procedure. Let us study the effect on the yield of wheat. We apply 5 fertilizers, each of different quality, on 4 plots of land each for the cultivation of wheat. The yield from each plot of land is recorded, and the difference in yield among the plots is observed. Here fertilizer is a factor, and the different fertilizer are called levels. So fertilizer is factor. This is a case of one-way or one factor ANOVA, since there is only one factor which is going by the name of fertilizer. We want to test the effect of fertilizer on the 4 plots of the land. We may also be interested in the effect of fertility of the plots of the land, but in that case we factors fertility and fertilizer. That is the case of two-way ANOVA. Similarly, you can add a third factor like rainfall and become 3-way ANOVA. So ANOVA, we can concentrate on the same factor again, and that is called a balanced one-way ANOVA. If you are concentrating on not one but 2 factors, that is known as 2-factor ANOVA. Chance cause and assignable cause. In the above experiment, the yields obtained from the plots may be different, and we may be tempted to conclude that difference exists due to difference in quality of the fertilizers. But the difference may also be the result of certain other factors which are attributed to the chance, which are beyond human control. This factor is termed as error because we are not concentrating on those factors. So the difference of variation which is existing because of the error can be attributed to a chance. So the estimated amount of variation due to the samples as the chance causes are obtained separately or compared using an F test, and conclusions are drawn using the value of F. So some causes, some errors are, some are assignable. If you are able to identify a particular cause which can cause a difference which is going to exist, then it is an assignable clause because you are in the know of the clause that is being exist in that place. But a chance cause happens merely by chance and not by human error. Now we have come to the conclusion of ANOVA. One ANOVA. ANOVA, I will finally do the difference between a t-test and ANOVA and why ANOVA is going to be used in place of a t-test. If there are two groups, two samples from the same population or two independent populations, we can use t-test to derive whether there is any significant difference between the mean and variance. But if there are more than two groups available either from the same universe, same population, or from independent populations, we cannot use t-test because there will be requirement of multiple t. So in that case, it will be very clumsy, very difficult for the calculation, because if there is 6 groups, then you are required to calculate 70 t's. So it will create problem researcher. So instead of using a number of t-tests, we are going to use only one ANOVA test, which will qualify the result, which can quantify the result and qualify the result whether there is any discrepancy actually between the mean and the variances of different groups, which is a result of being derived from same population or the other populations. But remember, if still you decide that you are going to use multiple t-tests and some other person, another student, is going to use the ANOVA, the end result is going to be the same. So a multiple t-test is equal to ANOVA, but instead of doing a multiple t-test, it is able that you use a ANOVA test. ANOVA will be simple and much simpler in fact than using multiple t-test. Come to the first part of discussing ANOVA. In the next session, we'll do a ANOVA test. We'll see how ANOVA can be utilized to correct two factors includable in the same population and in the group. So till then, I hope you have understood the concept. You should be able to practice, and in case you have a problem, please come to us. Thank you very much. Thank you.